All right, so thank you for joining us this evening. If you have not been on with us before, this is Illini Aero Connections. This series was started as a way to bridge the gap between our alumni and our students, and to really address some topics that maybe aren't fully covered in the classroom, and that will help our students as they look forward to their careers and to leaving Illinois. So tonight we have 4 great panelists on with us, and we have Caite Beck moderating for us in place of Samantha McHugh. Caite has stepped up, so thank you so much for doing that, Caite. And I'm going to turn it over to you.
Great, thanks, Courtney. As Courtney mentioned, today for Illini Aero Connections, we are doing our propulsion and advanced design topic. We have 4 alums who are heavily involved in that area of industry and are here to talk to you guys today. We have Paul Dees, who obtained his BS in 1981 and MS in 83. He's a Boeing Technical Fellow and Airplane Configuration and Integration Specialist. We have Aaron Perry, who obtained his BS in 15, MS in 16, and PhD in 2020. He is in Research and Development Engineering with Whisper Aero. We have Sahithi Kalidindi, who got her BS in 2013, and then went on to get her master's as well. She is a business development leader for GE. And then finally, we have Daniel Uhlig, who got his MS in 07 and PhD in 14 in aircraft, and is an aircraft configurations group lead for Aurora Flight Sciences, which is a subsidiary of Boeing. So I'm not going to take up all of their time. So I will allow them to speak a little more about their experiences and what they have accomplished in their time since graduating from the University of Illinois. If each of you panelists would be so kind as to maybe give a slight elaboration on just beyond your title to help explain what it is you've worked on and specifically related to propulsion and advanced design. We'll start with Paul, if you don't mind.
Hi, just a sound check. You can hear me okay?
Sure can. Thanks, Paul.
Okay, awesome. So I graduated with my master's on a Thursday. I got married on Saturday, and we flew out to San Diego for our honeymoon. And then a few weeks later, I started as a flight sim test engineer at Northrop. Was at Northrop, and actually most of my time at Northrop was in aerodynamics, a couple years, and then we went to St. Louis. I worked for McDonnell Aircraft for 5 years, and then came out to Seattle for Boeing. And after I came out, then Boeing and McDonnell merged. And so that was kind of fun. Worked on either aerodynamics or airplane config design on over 20 different aircraft projects, varying from hang gliders all the way up through supersonic transports. So it's been really fun to be involved in that. Lately, I've been spending the last 3 years on the Boeing NASA X-66, the sustainable flight demonstrator that's a transonic truss-braced wing. And back to you.
All right, and Aaron?
Hey there, I'm Aaron. Yeah, so I was at UIUC for a total of 9 years, from 2011 to 2020. Did bachelor's, master's, PhD in that time. And all my grad work there was with Phil Ansel, who I see has joined us. Thank you. I was studying distributed electric propulsion using experimental aerodynamics methods. So I did a lot of wind tunnel testing and flight testing, identifying aeropropulsive coupling mechanisms when you have ducted fans tightly integrated with wings. After graduating, I went out to the LA area for about a year and a half, and worked at a company called AeroVironment, basically doing flight testing and aeromechanical design work for UAV systems for the armed forces. That really wasn't my thing. So in 2021, decided to do something crazy and join a startup. Whisper Aero had basically just announced that they were a thing, and I was very excited because a lot of distributed propulsion stuff is highly related to the work that Mark Moore had previously done at NASA. So I joined there. I've done a lot of things there. I've spent about half my time developing ground test software, hardware, sensor instrumentation, things like that. The other half of my time I've spent doing like aerodynamic design and analysis, from like fan system level things up to more like aircraft integration things. So yeah, that's me.
Cool. Thanks, Aaron. And then Sahithi.
So I wasn't at U of I as long as Aaron, but Phil Ansel did teach one of our undergrad classes when I was at U of I. Right after I graduated, I went to GE Aerospace and I went through the Edison Engineering Development Program. And I got my master's through that. A big part of the curriculum was highly turbo machinery focused, with GE instructors like previously from GE teaching many of the courses. And then within GE, the roles that I've had kind of spanned across commercial aircraft engines with LEAP, which is on the A320neo, as well as the 737 MAX, GE 9X on the 777X, a lot of military aircraft engines between the XA100, which is the first ever adaptive cycle engine in the world, the F110, F101, F118, J85, TF34, and I also worked on marine and industrial engines. I've had roles kind of spanning across the life cycle in design engineering, all the way from like the pre-CDR timeframe where you're literally developing the engine architecture all the way to after DDR and engine tests to fielded products. I've had roles in heat transfer, engine performance, engineering management, and now I'm in a business development role as a senior technical leader at GE Aerospace. And my job today is really working on those business development activities with DARPA specifically. My role at GE is to be the voice for DARPA within GE and then advocate for GE within DARPA and really like advocate for the technologies that are strategically important for both organizations to deliver what the DoD needs, today and in the future.
All right, thanks, Sahithi. And then last is Daniel.
Hey, Daniel Uhlig. I've graduated my PhD in 2014 and left Champaign-Urbana to come to work for Aurora Flight Sciences, which is then a small independent company, just under 500 people. We could still do SBRs back then. We were bought by Boeing a couple years later. So now we're part of big Boeing. Aurora people support X66 with Paul Dees. So it's kind of funny how we exist in a big world. I've worked long endurance, high aspect ratio work is where I started. Flexible wings and very flexible wings, and understanding the aerodynamics and the structural elastic response and how to design those sort of things. I've worked in performance, aerodynamics, and aircraft configuration since then. I've worked some electric eVTOL, and now most recently I'm supporting the electrified propulsion demonstrator effort with NASA. So it's a high-powered hybrid electric aircraft, and so working the challenges there and making sure it's integrated and working.
Great, thank you. And thank you again to all our panelists. So as far as organization for this, I'll go ahead and ask the first question, but if the audience has a question throughout, I'm monitoring the chat. If you want to type your message, you're welcome to raise your hand and I can keep track of that as well. And you can unmute yourself and ask in person if you prefer that. And Courtney, I may need your help in case I do miss someone, but I'll try my best to keep an eye on the participants to see if anyone raises their hand. So while you guys, the audience, are thinking of questions, I'll go ahead and get started with describe how your undergraduate curriculum prepared you or maybe didn't for your role in the industry. And to our panelists, I guess you can unmute yourself and talk as you see fit if you find a question resonates with you.
I think it taught me how to think as an engineer. How to think is a pretty important thing, and it sounds kind of esoteric, but I'll give you an example. In my second semester chemistry class, I remember wondering, I don't think I'm ever going to use this again when I work in industry. And in my higher order math classes and physics, I thought the same thing. And I was correct. I haven't actually applied that directly, but I work with people who do apply it directly. And the logical, sequential thinking, but also the balance between paying attention to detail versus big picture, all of that, all of those skills really evolved from those classes. So they were still pretty valuable.
Right. Okay, I would agree. For those of you with a PhD specifically, how did this advanced degree help you in the industry? Perhaps you can even do a compare and contrast with the academic environment that you were ingrained into and then the industry environment that you're in now.
I think with the PhD, and I guess maybe it goes back off Paul Dees, even it taught me a little bit more how to think and how to attack problems. I haven't every once in a while I apply details in my research, and it's fun, or techniques that I do in my research, and that's fun. And I definitely, it's much quicker to do that than other things. But then I also spend a lot of time working on problems that I'm not familiar with, or helping people work on problems that I'm not familiar with. And so this involves a little learning, break out a textbook, find an AIAA paper, and work through it and understand how that problem should work and how the physics should work, and go through that. And so I think that's a bit of what Paul Dees was saying with, learning how to think. And I think the PhD is just more learning how to think and learning how to set up an experiment, learning how to set up analysis.
Yeah, I totally agree. And then I guess add on my front, like, for me, the topic of my PhD is, it kind of extremely relevant for what I'm doing right now, and probably the largest reason that, like, I was hired into the role I have. And I'm basically doing kind of continuation of that research, but it's more on like a business motivated front, I guess. So I think, like, part of it was maybe lucky. I got interested in a topic, and found Professor Ansel, who had that topic there. That really opened up a lot of opportunities, because there's a lot of companies that are interested in electric aviation and distributed propulsion and things like that. So I think it can also help, if there's an area that you really want to work in, getting a PhD there certainly gives you a lot of credibility.
Did you know when you entered into your PhD program that was what you would ultimately want to enter into the industry under, or did that kind of come to you while you were pursuing that specific topic within your PhD?
I don't think I planned for it. It's actually kind of ironic. I met Mark Moore, who's the CEO of Whisper now, at a grad student advisory committee thing back at Illinois in 2017. And I was asking him, I was trying to decide if I should do a PhD at that time. And I was like, oh, I'll ask this NASA guy. And he's like, oh, you should only if you want to teach, or if there's a startup you want to join that really needs a certain skill set.
Mm-hmm.
I was like, oh, whatever. And then now I'm working at his startup, which is, I don't know, I think it's funny.
Yeah, it kind of speaks to the importance, I guess, of networking too. Sorry, I didn't mean to step on you.
You're good.
So Daniel, go ahead, Sahithi.
I was gonna add one more thing to the comment that Paul Dees made earlier. The other thing it was really helpful in was understanding the fundamentals, the fundamental incompressible, compressible flow equations, beam bending problems, things like that, because even though some of the problems that we're working on today are more complicated, there's a lot more systems involved. Like even the big problems can be broken down into smaller and smaller components. And are there ways that you can simplify these bigger problems into like an easier to understand, like undergraduate level problem, and really be skeptical about like your CFD models, your FEA models, and things like that. Like I wasn't an expert in any of those, but I was a design engineering manager responsible for people that did that type of work, and being able to be really skeptical about, are the results they're showing me, do they make sense from a fundamental physics level or not? That's something that the things that you learn in your undergraduate curriculum can really help you. And I literally have like a sheet of just like fundamental 1D equations on my desk at work that I look at on a pretty frequent basis, just to, you know, make sure that, hey, the things people are telling me, do they pass the sniff test or not?
I used to be in analysis, and we had a saying that said all models are wrong, but some are useful. So how have you guys been able to expand upon what you're talking about, Sahithi, and opening up to everyone? How have you been able to bridge that gap between what some would consider to be of course, very complicated when you're learning it in your bachelor's. However, you learn that the real life applications, once you remove all the assumptions that are made when you're doing those fundamentals, as you mentioned, Sahithi, it makes things far more complicated. So when you guys are developing these new technologies or improving upon existing ones, how have you been able to modify or extend or develop these new tools to be able to accurately depict the challenging examples that you guys are working to create?
Let me give you an example from multidisciplinary analysis and optimization. Talk about complex modeling. I mean, that MDAO is amazing because you're combining, in the case of Boeing, we combine higher order methods from multiple engineering disciplines. We throw in a bunch of design parameters and constraints, and we push a magic button, and some who are not familiar with MDAO expect that it's going to design the airplane for us, but it's really a giant mathematical exploiter. And so what that means is what Sahithi was saying, if you as an engineer don't understand the foundational first principles, whether it's 1D flow or strength of materials or basic flight controls, if you don't understand that, you're going to get led astray by one of these fancy tools. And it's going to give you the wrong answer to the 14th decimal place. So it's really important to have that foundation, as well as advancing our tools, because the beauty of MDAO is it can do the work several orders of magnitude faster than a team of engineers. And the downside is that if you're not smart at how you constrain it, it will just lead you astray.
I guess I was trying to think about, there are a few examples I could pull here, but if we're looking at flight mechanics or performance type things, and we're running through it, and we're getting everything kind of follows the trends we expect, and then all of a sudden something weird happens. You have to be able to identify, a lot of the times it does follow the simplified models, and maybe the line isn't quite as linear as you'd expect, but it's still there. But then something will cause, there'll be an abnormality, and then you have to be able to say, yes, that's an abnormality. Why is it there? And go back, just don't blindly believe the dump of the CFD. Go back and look through, pull out the sims that are showing this weird behavior and look at it. Half the time it's the sim having a weird weird convergence problem, and half the time it's actually, well, there's the flows interacting in a way you didn't think about it, and it's not a textbook example, but once you look at the visualization, you go, oh, okay, this makes sense. And so it's the simplified problems are the simplified problems. The simplified problems from school are the simplified problems you'll see in work, but you have to you have to be ready to know this can be complex, and where it's complex, and be skeptical in the right spots, and be able to figure out why it doesn't follow these simplified problems. Is being able to understand that's important.
I was going to say, I think maybe this is kind of implicitly included in what Paul said, but you know, you learn like these simplified models in undergrad, but when you go to design a very complex system, you are going to get the wrong answer if you don't couple the disciplines together. So kind of exploring that has been very cool for me. You know, how do we bring multidisciplinary analysis into like conceptual design phases and earlier phases in the design cycle?
Yeah, one specific example I have was there was a propulsion class I think everyone had to take in undergrad at U of I. It was like A433 or something like that, where it walked you through an aircraft engine and you had to like predict the performance, SFC, and thrust for an engine, and it was on either like a commercial or military aircraft engine, but it was very, you know, high level. It just treated the aircraft engine as like a black box compressor, then a combustor, then turbine, but you know, didn't really learn about the secondary flows aspect of it, all of the cooling systems that you need, all of the oil systems, fuel systems, lube systems that all go into how does it affect the heat transfer of the engine, as well as, you know, the overall engine performance. And then as we started to progress into more complicated engine architectures like adaptive cycle engines that have multiple streams, how do you you can't rely on the basic mixing flow assumptions. So there's also the validation piece involved, where you have to actually run a test, understand the test data, actually learn how to model these unique systems that are non-traditional.
Yeah, that's a good point. I think that speaks as to why MVSE is so big in the industry right now too. Okay, so changing topics slightly. I don't know if you've heard of this guy, but Philip Ansel wants to know what does the future of aircraft and propulsion technology look like? He claims he's asking for a friend, but I figure the four of you would be able to help answer that question.
I can I think you'll get a different answer depending on who you talk to, but I'll try to talk about a technology that probably the others won't talk about, which is adaptive cycle engines. Basically, we have commercial aircraft engines that have these pretty huge fans that are optimized for fuel consumption, you know, low SFC, and then you traditionally have military engines that are, you know, smaller, primarily designed for high thrust, don't really care about how much fuel you get. Well, if there was like a conflict in the Indo-Pacific, which is highly relevant right now, one of the things that the military is highly focused on is range, and even the commercial industry with sustainability and fuel consumption is focused on lowering your fuel consumption as much as possible. But how do you get you know, a highly fuel efficient engine that's also, you know, high performing, high thrust? So that's what adaptive cycle engines are, a transition mode that you know, goes from a high bypass ratio engine to a low bypass ratio engine, being able to operate at every single flight condition with the usage of, you know, more variable geometries than you can count on one hand, that need to be working in concert with one another so you can optimize at every single design point. There's also convertible engines that, you know, convert from turbo shaft to a turbo fan engine, which can be helpful when you're in a distributed lift fan, distributed propulsion type of scenario. There's a DARPA program, DARPA Sprint, which is focused on high-speed VTOL applications for medevac helicopters, where you're lifting troops out of Pacific Island type of situations, but you also need it to be able to go much faster than a helicopter would. And in those cases, it would be really helpful to have a turboshaft engine that you can have a gearbox that powers a bunch of generators that power the distributed propulsion system, but also be able to turn into a turbofan that can provide the thrust that when you need it to go horizontal flight. So those are some unique concepts that are on my radar for kind of the future time frame.
I guess my answer to that question would be that it'll be quiet. So I'm fully focused on electric propulsion. So there are a lot of cool things going on with the gas engines as well. So in case you don't know, Whisper Aero is kind of focused on developing quiet electric ducted fan technology that's also very efficient. And to accomplish that, we've really looked at a region of the fan design space that all of the large engine manufacturers really haven't looked at before. And I think we've kind of pulled off our goal. We've managed to develop an electric ducted fan that is significantly quieter than systems that are of equal capability. And it's really cool when you hear it. So I'm personally very excited for when we can get some of these quiet electric systems up in the air. I think it's going to be a really cool experience for people to hear that. And you can hear a sneak peek if you go to our website. So you should do that.
Cool. I think the future is going to include, if we think about commercial airplanes, we have to find a way to get more wingspan to work. So our folding wingtip on the 777-9 is, I think, portending what the future will look like, because our airport infrastructure is likely not going to change even if our wingspan grows. And what that points to is sustainability and more use of sustainable aviation fuels. And on commercial airplanes, there's talk of autonomy. I'm a little skeptical about that, because I've ridden jump seat in a commercial airplane flight test and been absolutely amazed at the pilot workload. And I can't understand how autonomy could work for that. But I'm hopeful that we can find ways to reduce pilot workload and maybe create opportunity for that. So for commercial airplanes, it looks pretty cool. And by the way, Sahithi, I'm pretty interested in that variable cycle you're talking about, even for commercial airplanes. I know it has great application for military airplanes. So
yeah,
go ahead.
I was gonna say one of the engine programs we're working on that took the military technology and adapted it to the commercial space is the RISE program. It's an unducted fan engine that has multiple streams as well, that we're trying to get into the field that we're doing early development on right now. And one of the challenges, tying back to Aaron's comment about noise, that's one of the issues there, where it's highly efficient because it's an unducted fan, but one of the challenges is because it's unducted, there's a lot of noise challenges that we're dealing with right now.
I also want to give a shout out to, given that I work for a huge company, a shout out to the startups, because without our startups, that's really where a lot of innovation happens. I mean, I work for Boeing, and sometimes it feels like there's a corporate immune system that when you come up with something that you think is pretty cool, there's a dozen people coming to pour cold water on it because they're threatened by it or something, something silly is happening. But I've had the opportunity to work with Aurora. And before that, I had the opportunity to work with Ariane on the supersonic business jet. And previously, I've worked for very small companies. And there's a dynamic that happens in a small company that is more conducive and more free to making cool things happen. And at the Boeing company, we have little pockets of it. So don't take my words the wrong way. Boeing creates a lot of amazing innovation. And I'm feeling that right now on the X-66, that we're doing stuff that wouldn't happen at other places in Boeing because we're in a climate where it's encouraged. So I think that's a big part of the future, is that balance between small companies and large companies. And so it's not a technology so much as a human element to it.
Yeah, I think a lot of things that at least I didn't understand as an undergrad too, Paul, to your point, is that these larger corporations will frequently partner with small companies or startups to help them integrate their innovative technologies into existing systems that the larger corporations have had the time to fully develop and bring to a further along in the life cycle. So I think it's good to emphasize that that's a potential career opportunity as well for our undergrads who may be on the call.
We're doing that right now in a couple of areas. So GE traditionally big commercial aircraft engines, not really in the ramjet, scramjet space, but recently we acquired a company called Innoveering that has a lot of really cool experience in that area, as well as plasma propulsion. And then we're also partnering with Florida Turbine Technologies, part of Kratos, who has more experience in smaller engine classes, because the way, at least like on the military side, the way the trends are going, especially with like war in Ukraine, primarily smaller engines for drone applications rather than bigger engines for F-16s, F-15 type of aircraft. So we're trying to get more into that space. And the thing is, GE, with like the current mindset we have with delivering a ton of commercial engines, is we design things that are really expensive and last forever. We're not really good at doing cheaper things that are smaller, lower cost, that don't last as long. Mm-hmm. So the small businesses really help bring in that agile and nimble mindset at solving problems, quicker without the bureaucracy. And one of the challenges that I see, especially with these acquisitions, is I don't want these companies that we bought to, change their culture and add more of the bureaucracy and rules. But one of the things big businesses bring is just resources from a technical standpoint and a career development standpoint that I think has been really helpful.
Sahithi, have you found that, since you've worked both the commercial and the military side, and this question expands out to whomever has potentially worked both sides, that the agility that is necessary right now in a military environment, specifically with the current sociopolitical environment and what's going on, that, like you said, requires quick turnaround. Do you find that that is becoming more prolific even in the commercial space, or do you think that overall that industry is staying in a condition in which the longevity is more important? I'm thinking like the commercial airlines, where they want their engines, if possible, to last as long as they possibly can until they're, no longer usable. So, but do you find that some of that mindset may be shifting, or do you still think that there's this dichotomy between the agility that you can find in the defense industry versus the more stability that is typically found in a commercial industry?
Yeah, so my opinion is it kind of varies, right? Because commercial, a lot of our design practices within engineering, they're more tailored towards commercial engines and the safety thresholds that you need for the commercial engines. So circling back and say, hey, it doesn't necessarily, satisfy this requirement because the Air Force or Navy has agreed with this risk. Even in manned aircraft, we're finding that the risk levels are different for an aircraft that's manned by 1 or 2 people compared to a passenger aircraft with 300 people. But that being said, the commercial side can move pretty quickly because a lot of the commercial efforts are almost always company funded efforts, which means the company has 100% control over the destiny of where the products go and how you execute on them. The military side, I think the problem, it's not so much the over designing is a problem, but the other problem is because so much of it is dependent on the government life cycles and the congressional budgeting process. A lot of programs can start and stop, and then you have to restart, certain designs that you've already executed on because, this person left and you don't know where they left off. I feel like that's what kind of extends the timeline on the military side more so. That kind of adds to the challenge.
Awesome, thank you. I'm gonna switch topics again a little bit. I'm gonna go to one of the questions from the audience. So we have a question from, let me scroll up and get the name, Chaitanya. I apologize if I mispronounced that, but in undergrad, we are working on 1D and 2D models for ideal conditions. You guys kind of touched base on this before, but however, realistic assumptions may not yield same results. So how can an undergrad, to address this audience specifically, start to get accustomed into the quote unquote industry way of doing things? Meaning, how could they potentially be adapting their models maybe now to solve realistic problems in the current environment that they are in?
I think quite often we do the opposite. We have a very complex problem and we try to find out what 1D or 2D simplified model we can run that at least gives validity check to whether it's CFD or FEM, and does the validity check so we can get agreement with it and understanding. So sometimes it's a little bit of the reverse. We look at this and we go, hey, is this really just a 1D beam bending problem? Okay, let's just look at that real quick and help us get in the ballpark before we go analyze things more. Maybe that's a backwards answer to the question. I think.
No, I agree with you, Daniel. Like I've, as you were explaining that, I have like a very specific example where we had to do that, where there was a field issue that we had that, stemmed from thin walls in a cast part. And we had to figure out, what the population was and could you have this problem on, other engines and like make assumptions on, the wall thickness. And then we started with like the 1D model and see if like, hey, could it withstand with, this crack assumption? And then we were like, no, this doesn't satisfy it. And then we just kept diving deeper and deeper until we did like a 3D crack propagation analysis, pulled all of the mission data from Boeing and the different allied air forces that were using these engines and seeing if, the way that they were flying it today still, allowed us to keep the engines in the field or not. And it literally got down to doing like the highest, most detailed level of analysis with like crack propagation, creep, like high cycle fatigue, low cycle fatigue, like all these different analyses. And the result was the fleet leader needed to, at the next service interval, like do a bore scope inspection in order to make sure that we didn't pull it from the fleet. But we started out with like the most basic assumptions and then kept going deeper and deeper because it takes resources and time to build more complex models. So if you can do it, you know, in a 1D, like basic ideal assumptions, then do it.
One other thing that I've seen, which I don't know if I'm a huge fan of, but basically you take the simplified 1D model and maybe you have some real data and you can apply fudge factors or knockdown factors to various parameters or quantities so that the simplified model then matches your data. And then at least you have, you know, a model you can run quickly that you feel is pretty confidently accurate in at least in the range of the data that you took. So you can do things like that as well.
I mean, I guess from a more practical point of view for the question, you know, learning and being familiar with things like CFD or FEA is helpful. And so, you know, if you have an opportunity to do that and to work on that a little bit and to get kind of familiar how things are set up, I think that's really helpful. But I think some of the ideal conditions are still, you know, will teach you what the derivatives are and what the trends are, and then, you know, you have to go do the detailed you know, structural analysis or, you know, circuit board or thermal or whatever it is. But yeah, and if you can get exposed to some of those more complex tools, you know, a lot of the people we hire have some experience with some subset of those complex tools before they get into industry. So having that experience is really helpful.
And also, there's CFD, there's finite element, there's also the CAD and the computer-aided design. I mean, there's a whole bunch of designers at Boeing that effectively draw stuff. You know, it used to be done on a drafting board, but now we do it in CAD. And the relational design of that, where all the models are linked together, you know, it becomes a digital representation of a physical reality. And one of our observations is that when you look at output from CFD, finite element, CAD, whatever it is, and you get these beautiful color contour plots, that there's an implied credibility that comes from that says, this is truth, this is engineering truth, this is good, rock solid gold data. When in actuality, there's limitations due to, in the case of CFD, the flow physics in the CFD. You know, you can look at full potential flow or potential flow CFD, and if you don't understand the limitations of it, you're going to get yourself in trouble. So learn as much as you can while you're learning these methods as an undergrad. What are their limits? Where do we run out of accuracy? And where are some test data that we can run test to theory comparisons? And by the way, what are the limitations of the test data? One practical example from aviation history: during World War I, most of the airplanes had very thin airfoils because the wind tunnel data at the time said thin airfoils are really good. They're better than thick airfoils. Well, the reason was the wind tunnels had a high level of turbulence in them that led the test people astray. And it wasn't until the thicker airfoils came along that they realized, oh, these are actually better. And we never looked back on the thin airfoils after that. So that was an example where test was leading us astray because of limitations of the test. So if you have a chance as an undergrad, spend some time in the wind tunnel at U of I. Just get your feet wet, dive in, right? And some of these other tools and methods, go for it. Learn as broad as you can, and then find something that you like and go deeper into that.
Yeah, that's always good advice. It's interesting to hear you talk about the importance of being able to challenge assumptions and to know when what you're assuming may be leading you astray, if it's whether it's the model or whether it's the test data. It's also interesting for me to hear Sahithi talk about this full-blown high-level analytical study versus say Aaron, who is sitting there saying, oh, you know, if you have some numbers, you can kind of get a good enough model. I've experienced this myself, where the classic analysis paralysis, where you are stuck in a cycle of always doing models and never actually making a decision and just going with it. How do you, all four of you, navigate the challenges of that in your different environments? Some of you at a startup, some of you at a larger corporation, when all of you are trying to be innovative and insert yourselves into new spaces within the industry.
I think for me, the answer is including frequent tests in that cycle. Like, we have a big focus on rapid prototyping. So we develop something new, we make it very quickly, we can run a test, we can compare that to models. Like Paul said, there's details there. We have to have confidence in our test data as well. But yeah, I think it's very important to include test data as you're developing new technologies as often as you can.
Yeah, as I think about, you know, the question of what is done is a really challenging question for the engineers, because in reality, when you're an engineer, you want to, your objective is not to have a job, right? To analyze this thing, be done with this, have the wing design and pass it off to someone else and go away. And so, you know, then you're going to find something else to do. But, you know, to engineer whatever the task is in front of you to done, and, you know, you can keep analyzing it for the rest of your life, but at some stage, you're done. You have to move on. You've done well enough, and so there's a lot of work there. I think, you know, we try to be innovative and try to, you know, balance analysis with risk, and a lot of it is test. You know, we're staring at a problem right now, and we think we have a solution. We think we know what the answer is going to be, but there's a lot of questions around it, and the solution is to try to move up the test. And even if it's not the final representative test of what we're actually going to do, can we test something very similar much earlier in the schedule? And so we're trying to get close enough hardware to test, you know, in the next few weeks, as opposed to wait till next year. And then maybe the last point is using multiple approaches. So if you're trying to get the drag of an aircraft, you know, you can use your CFD, and you can build up excrescence drag. You can also go back, how does this line up with other past work? You know, does the CFD drag look similar to what I get from AVL? And so, you know, those sort of things, if you have multiple answers and they're all starting to converge towards the same answer, you're probably right. You're probably in the ballpark of where you want to be. Yeah.
I think making sure you start with the requirements is really important. Like, what are you trying to actually achieve in either the product that you're trying to design or part you're trying to design? Like, what's your end goal? And then work backwards in, like, what level of analysis do I need? What specific tests do I need to mature this technology to, like, a higher TRL? And then making sure that you also factor in what are the manufacturing limitations. And because I see too many times people will design a part, run it through their models, but then they don't necessarily look into, hey, what do I actually need to do to attach this part to this other part, right? and like, if that gets found out too late, then you end up leading to a bunch of rework, a bunch of wasted time. Like, your models mean nothing at that point, especially if there's stress concentrators near, you know, the bolt holes or the attachment location. So starting with the requirements first, and then making sure that you have, like, a really structured plan on how to accomplish that requirement is really important.
Think of the value of iteration in the design of engineering. iteration is extremely valuable, but to an ignorant person, it looks almost identical to rework. And rework is basically fixing an error that could have maybe been avoided. So there's a difference, a strong difference between the two of them. And if you can keep your eyes on the prize, you know, you've got your requirements, they're mature, they've been vetted, they've been questioned and beat up and validated. Okay, here's our requirements. The prize is fulfilling those requirements with the minimum time and cost without further risk of a blow up happening later. And in the case of commercial airplanes, our complexity of our designs has just grown and grown and grown to the point where our previous paradigms don't work anymore. And that's best looked at when we look at, as a result of the accidents with the 37 and now what it takes to certify a future derivative of the 37 or the 777-9, it's much more complex. And so that fundamental engineering was done, but it's adding cost and time to the schedule to go back and make sure that our I's are dotted and our T's are crossed properly. And so it takes this ruthless discipline to drive for the prize. What is the prize? What does done look like? What's the minimum I can do to do it right with good first-time quality and be done? So there's this duality in our thinking. As engineers at U of I, we're bred and taught to care about the details, because if you get the details wrong, you'll get the answer wrong and you'll get a lousy grade, right? So that rewards detail. But there's also brevity in getting it done quickly with the right answer and finding the way to do that. So there's this duality, there's a conflict, and we got to find our way through it. So good luck to all of you. You're going to do that. You're going to find your way, and it's going to be really good.
Thank you, Paul. All right, I think we at least have time for one last question. Emma in the audience asked, what was something that you learned or experienced early on in your career that you have felt is translated, that is proliferated through the rest of your career, even to today?
I had a mentor that told me that everyone coming out of college is equally smart. Everyone gets the same degree, but the key differentiator between people is communication and your ability to talk about a technical idea or concept or anything at all levels, like at the highly detailed level, but also kind of almost like a 5-year-old can understand. And that really helped me in situations where we had conflict between teams, between suppliers that were outside of GE that either didn't want to share information that would be critical in solving a problem, but being able to explain the problem to a level that people without engineering degrees on the shop floor can understand, so that they can be part of the solution. And that's really been invaluable, so that you can really build more diverse teams with skill sets that you really need to solve the problem.
Yeah, communication is really important. And communication is a two-way street. You'll be talking to don't have much of a structures background, but I've talked to spent many time, trying to understand structures people and how they're worried about the stress or in this concentrations in this part of the spar, that's part of the spar, and how to compromise and where to put holes and that sort of thing. And so being able to explain yourself and then listen to them and have the fundamentals to be able to say, hey, this is what they're worried about, translate that back into your cheat sheet of formulas on the wall, to be able to understand what they're talking about, what they're worried about, what the relationship is. And so it's communication is a two-way street. You need to explain it, and then you also need to be able to kind of listen and understand other technical disciplines. Yeah.
I think more than communication, it's also, and we touched on this earlier, about understanding the fundamental physics behind whatever you're working on, whether it's flow physics, which would be translate to aerodynamics or fluid flow, maybe even hydraulic flow, or it's the physics of strength of materials and when something's going to break and how much margin there is in the structure. But we use a phrase at Boeing, we call it business physics. And we kind of smile when we say that because we don't really learn much about the business side when we're undergrads. And people that go on and get an MBA learn more about that. But it has to work for the business of whatever company you're working for, unless it's purely a research grant or a research capacity. So being able to know that it's okay to stop working on something that isn't going to pay off. And that's really hard. It's a real heartbreak when that happens to you on your first project, that they come in and say, hey, we're done here. We're not going to pursue this. The good news is we need you over here now to work on something else. And so I would say also be ready for change, disappointment, agility, and that kind of thing, that to be flexible, to grow in that. Thank you.
Oh man, I still feel like I'm early in my career, so maybe if you come back in like 10 years, I'll have more awesome wisdom. But I was gonna say something similar to what about.
We lost Aaron, I think.
I was to say, did he freeze for you guys?
Yeah.
All right. Well, we may just have to end on what Paul's note was, which is a good place to end. But I feel bad now that Aaron doesn't get to say his piece. All right. Yeah, I don't think he's coming back. Okay. Well, last question was, this is not a full question. This is just a yes or no. Is it all right if any of the audience has any questions for you for more insights, if they could send you an email or reach out to you guys? Courtney, if the panelists are okay with it, I'm sure you can distribute that information to those who need it or ask for it.
Absolutely. I'm happy to facilitate that as long as everyone is okay with me making those connections.
Lovely. So right to the person who asked in the audience, if you just reach out to Courtney, I'm sure she can give you that information. As for our panelists, thank you so very much for taking the time this evening out of your busy schedules for talking with us today. We really do appreciate it. Courtney, is there a future date on the schedule for one of these, or is that it for tonight?
So our next session, we don't have the date nailed down just yet. It's going to be in January. We're still working on dates with some of our panelists. So be on the lookout for that. I believe our next session will be on unknown trajectories. So alumni who took a little unusual path and did not stay specifically in the aerospace industry. So thank you to everyone who joined us tonight. Thank you very much to our panelists and to Caite for giving us your time and your expertise this evening. For everyone else who is on, you will see a survey come out in just a few minutes. We'd love to get your feedback on this session and on what you'd like to see in future sessions from Illini Aero Connections. So thank you all. Have a great night.
Thank you, everybody.
Thanks.
Bye.
Bye.